So I wanted to start by talking about the notion of proof. Okay, so what is a proof? If you studied a little math, then in mathematics we have proofs. So there are some axioms, there are some rules of logic, right, which we can use to derive to make like steps, and like a proof is a sequence of certain valid steps that reach the desired conclusion. But here I want to switch to a more computer sciencey way of thinking about proofs. And the computer sciencey way is a proof is something that allows you to cheaply verify some property. Okay, what does it mean? Proofs, they might be very difficult to obtain, but they are very easy. They're kind of defining properties that are very easy to check. Someone gives you a proof, then just a mechanical process of checking the steps. You can write an algorithm. It will be a very efficient algorithm that checks the proof. So if someone gave you a proof, you know that something is true, right? This is kind of, in some sense, conceptually what I'm going to think of as a proof. And this inspires, in computer science, the notion of, well, different names, but what's called the complexity class NP. So NP is really kind of the computer sciencey way to talk about proofs. There's going to be a more general way that we'll learn about later. So what does it mean? Suppose we have some problem. So we have some inputs, and every input can either have a property or not have a property. So for instance, inputs can be some strings of bits. This is just mathematical notation for strings of bits. If you don't know what those letters, this is just, and you have some subset of this. So the things that satisfy your property. And then there is some notion of a certificate that the property holds. So what does it mean? It means that we have some algorithm called the verifier. Okay, so the verifier, V, is something that can take two strings of bits and output 0 or 1. So this means that we have a program. It has some input, which is like some object that we want to ask some property of. We'll soon have examples. And we have a proof, and the verifier says, okay, verification passed or verification failed. And this algorithm has to be an efficient algorithm that runs quickly, so in polynomial time. So polynomial can be of n squared, n cubed, and 4, whatever, but not like 2 to the n, right? And so such a language L is said to be an NP if there exists such an efficient verifier, such that X is an L if and only if there exists some short proof, so some proof which is an element of strings of length, at most some polynomial in the length of X, such that V of xy equals 1. So if you're scared by the notation, then I will just explain it in words. So this, what I wrote here, just means that an object is in the set, this is called the language, if and only if there exists a proof. So there exists some string of bits, which is not allowed to be too long. Because if it was really, really long, then verifying it would also take a lot of time, such that when we run the verifier on the object and on the proof, the verifier says good. So if there's no proof, then it's not an L. And if there is a proof, then it's an L. Yes?
What does a P, is that 1x1?
Yeah. Here, it's P of the length of X. So P is some polynomial, Yeah, there's just a notation for that. Yeah, sure.
So here is Y and X is the input?
Yeah. So let's just make some examples to make it more, this was very abstract, so just some examples. So for example, we want to know whether a number is composite. Okay, so L could be the set of all composite numbers. So then, what's a way to prove that the number is composite? If I give you two factors, which are not one and not a number, and you can check that you multiply them, I claim that 6 is composite, so prove it to me. So I give you 2 and 3, and now you can check that 2 times 3 is 6. So you know that 6 is composite. So there is actually an algorithm that checks directly whether a number is composite, but this is a very complicated, very non-trivial algorithm that was only discovered in this century. Yeah. Right. So composite numbers is one example. Right. Another example is checking whether two graphs are isomorphic. So what does it mean? So a graph is like a thing that has vertices and has edges connecting those vertices. It's called a graph in mathematics. So if I draw two different graphs, for example, I make a drawing like this, then what does it mean to say they're isomorphic? It means there's some correspondence between the vertices. For example, this corresponds to this, this to this to this, this to this, and this to this, such that it's a one-to-one correspondence. So it's in both directions, basically. And two vertices are connected by an edge if and only if the corresponding vertices are connected by an edge. So usually in computer science, we like to represent data in some form. So imagine that so it's not very good, but so graphs can be represented by matrices, right? I give you a matrix, a graph of 4 vertices. I can draw it as a matrix. And if the vertices are connected, I place here 1. If they're not connected, I place 0, right? So a matrix like this represents a graph. Now, suppose I give you 2 matrices, and I ask you, are those isomorphic graphs? This is not so easy to check, or it's not clear at all how you would check it without, checking all the possible permutations, which takes forever. But if I want to just prove to you, that 2 given matrices like this are isomorphic graphs, then I just tell you what the correspondence is. So vertex number 1 here is number 7 here. Right? Vertex number 2 here is vertex number 5 here. Once I gave you the correspondence, it's very easy to check where this is a valid isomorphism. So this is another example of of a proof in the computer science sense. Okay, and let's see. Right. And a further last example, if you want, is suppose that I give you a system of linear inequalities. So something like x plus y is greater than or equal than 7. X minus y is smaller equal than 3. I don't know, x is greater or equal than minus 5, something like that. And then I ask, maybe it's 2x to make it more interesting. I don't know. Okay, so linear inequality. And I ask you, does this system has a solution? An integer solution. Not just solution, but solution in integers. Where all the numbers are integers. Then again, how to know whether it has solution or no, it's at the very least not clear. But there is a very easy way to prove it. So if I just give you a solution, I tell you, okay, x equals y, y equals 2, z equals 3, then you can easily check. That's another example of a proof. But those were all really examples of languages in the class NP. So far so good, but this is kind of a very ordinary notion of proof, or we can call it a static proof, sorry. So the proof, the process of verifying the proof is there's just one step. Someone gives you a proof, you check it, either it's true or it's not true. So it turns out that we can talk about some more interesting and more general notions of proofs that can be more powerful in certain cases. And this is really the main topic of the talk today. So So now we come to some new notion of proof, which is called interactive proof. So what does it mean interactive? That now the prover, the one who's trying to prove something, and the verifier who's trying to check. And the verifier, it's important to remember, the verifier doesn't trust the prover, right? It's like, otherwise, if I trust you and you tell me something, then okay, I trust you. But the whole concept of proof is based on this, I don't trust you. Maybe you want to lie to me, maybe you want to trick me. And the notion of proof, the whole power of it is that even though I don't trust you, if you succeed to prove something to me, then I will come to believe it. This, in some sense, conceptually, is the whole point. So an interactive proof is when this verifier and prover are having a dialogue, okay? So imagine we have like a verifier and we have a prover, and they're talking about some object X, and they're asking, is X is an L for some L? So there's some data, and we want to know where some property about this data is true. And now they have some protocol according to which they talk to each other. So maybe V starts by sending some message to P, P sends a message back to V, and V looks at this message and sends an answer back, and they keep talking for 10 rounds, and in the end, the protocol is over, and the verifier declares, okay, I'm convinced or I'm not convinced. And also what's important here, and this is not obvious, but it's actually important, the verifier can do things which are random. So the verifier can decide to throw some coins and do something randomly in a way that the prover cannot anticipate in advance. And this is important. So, okay. So, and then, because it's a random thing, right, then given some input X, and given some strategy that the prover uses, we can talk about what's the probability that the verifier will decide to output 1, right? Instead of talking just verifier accepts, instead of the verifier just accepting or rejecting, there might be some probability it accepts, some probability it rejects, because some random things happen in the middle. So now, because we have probabilities, our requirement is going to be, so what's called a valid interactive proof protocol, right? What does it mean? This protocol is good. It has to have 2 properties. So one property is that if X is in the language, that means if the property we're proving is actually true, then there exists some strategy of the prover such that the probability of accepting is at least 2/3. Okay? So if the property is actually true, and I'm actually proving you a true fact, then I have something to do which would convince you with probability 2/3. Maybe I will fail to convince you, but there's at least a good chance I will convince you.
Now you need to define what a strategy.
Yeah, so I'm not going to write formal, this is not going to be like completely formal mathematics, but just imagine a strategy is just a way of playing this game, right? So strategy means that, given what previously occurred in the dialogue, what's the next message I'm going to send? This is a strategy. Yeah.
The probability of accepting is greater than 2/3 each time they do the process?
Yeah.
Independently or not necessarily?
I mean, the only randomness here, X is fixed. So X is not random. The only randomness comes from the fact that V sometimes flips coins. So because those coins are independent, if they're repeated, the probabilities are going to be independent necessarily.
It's not necessarily the case that you can, like that running it again gets you a second.
I mean, if the prover decides to change what it's doing, then maybe not. But if the prover forgets everything that happened in the previous round and just starts anew according to the same strategy, then it's going to be independent probability.
So we do require that.
We don't require it, just follows from the definitions. So
Okay.
Because the only source of randomness is the coin flips here, if we assume that the prover strategy doesn't depend on things that happened on previous cycles of the whole proof system, then it's necessarily the case that its probabilities are independent.
So then Well, why is probability of acceptance 2/3 and not greater than 1/2?
Yeah, so I'll get to it in a second. And the second property is that if the property doesn't hold, then for any strategy, the probability of accepting is at most 1/3. So if I'm proving you a true thing, then there is some way for me to convince you with probability 2/3. But if I'm trying to lie to you, if I'm trying to prove you a thing that's actually false, then maybe I will sometimes manage to trick you, but it will happen with, no matter what strategy I use, it will happen with probability 1/3 at most. So those exact numbers, 2/3 and 1/3, they are pretty arbitrary. It's only important it's bigger than 1/2 and smaller than 1/2, because what happens is we can always make those probabilities better by repeating the whole process, exactly what David said. If we have something that gives us particular probabilities, we can just repeat this 10 times and we get much better probabilities by just, taking a majority vote of the results or whatever. And this way we can, get any probability which is like polynomially small and still do it in polynomial time. Okay. So this is a nice story, but the first interesting question is, does it actually help? Are there things that are there proof systems like this, which are not just, which don't work in the static setting, but only work with those interactive things? Can we actually do something interesting? And the answer is yes. So the first example I'm going to bring is returns us to the question of graph isomorphism. Okay, so recall that we had like two matrices, right, which are two graphs actually. So they're like symmetric, let's say, because it doesn't really matter for this purpose, but they could be asymmetric. It doesn't really matter. So there's like two graphs, and there's like another graph. Like, I don't know, whatever. And the question is, are they isomorphic or not? So previously we've seen that there is a way to prove the two graphs are isomorphic by just showing you what the isomorphism is. So actually checking, by the way, it's not easy to just check without any proofs that they are isomorphic. Like if there's a polynomial time algorithm which just solves this problem, then there's trivially a way to prove it. You can just use the empty string as a proof, right? The verifier will just run the algorithm. But there isn't such an, we don't know. So the best known algorithm is only quasi-polynomial time. And that's also something that Laszlo Babai published in 2015, and it's still not fully peer-reviewed and whatever, but there's no known polynomial time algorithm for this problem. So there is the obvious way to prove the two graphs are isomorphic. Is there a way to prove that two graphs are not isomorphic? Notice that the proofs are asymmetric by nature, or at least static proofs are definitely asymmetric by nature. So proving that something is false is different from proving something is true. To prove that graphs are isomorphic, I just tell you which vertices here corresponds to which vertices here. How would I prove that they are not isomorphic? It's not clear, right? Not clear at all. But in interactive protocols, we can do it. And how do we do it? So suppose that suppose that the prover wants to prove that two graphs are not isomorphic, right? So what the verifier does in this case, the verifier randomly flips a coin to choose one of the two graphs. Then the verifier flips a bunch of coins to scramble this graph randomly, right? So if I have a graph like this, I can decide to relabel the vertices, and I get a new matrix. So this just permutes the columns and the rows. I get some new matrix. But I flipped some coins randomly, which you, the prover, don't see. You don't see what coins I get, what are my coin flips. And I get some new third graph. So secretly, this graph comes from one of those two, but I haven't told you which. And then I ask you, the prover, to tell me which graph did I use, this one or this one. If they're indeed not isomorphic, then you, as the prover, then, you know, if the prover doesn't have any computing bounds in the setting, only the verifier has. So the prover can say, yeah, this is isomorphic to this. And it will be true. But if the graphs started as isomorphic, then this new graph, if those are isomorphic, then this new graph is going to be isomorphic to both of them. So there's no way for the prover to know where I scrambled this thing or scrambled this thing. There's no information.
So we're assuming the verifier has unbounded compute in order to do this?
No, the prover has unbounded compute.
The prover has unbounded compute in order to do this. Okay, that was the...
Because, I mean, that's kind of analogous to how we usually do proofs, in the sense that, I mean, if someone gave you a proof, maybe producing this proof was very, very difficult, but you as the verifier, you should have an easy time of checking it. So here the proof is interactive, so the whole interaction might also be difficult, but you as the verifier has to have like an easy way of doing this, right? In this sense, it's like analogous to what we have in the static case. Okay. So we see one example where an interactive proof exists, but there's no obvious way to do a usual like static proof. But in fact, interactive proofs turn out to be really, really general and apply to a whole lot of problems, and we'll see exactly to how many. Yeah. So the next topic is we're going to talk about the complexity class PSPACE. So this is a very famous type of problems. So before that, we had NP, which are problems that have. So there's NP are problems that have proofs in the ordinary sense. There's IP, which is problems that have proofs in interactive sense. There's P, which is problem for which there's just an algorithm to solve the problem. You don't need any proofs. There's an algorithm that runs in polynomial time and solves it. So PSPACE is another important complexity class. And so PSPACE is polynomial space. So space is like theoretical computer science lingo for memory, right? So if you know programming computers, then you know that a program, it runs for some amount of time, but it also takes some amount of memory. So that's called like the space complexity. And PSPACE are exactly those problems that can be solved within reasonable space complexity. So reasonable, again, means that the space complexity is polynomial in the size of the input. Okay, so all the problems for which there is some algorithm that solves the problem with the amount of memory it uses is polynomial in size of the input. Notice that this is potentially much bigger than P, because the time it takes can be really, really long. Yeah.
Is there any bound on the time?
There's no bound on the time.
No bound on time.
Right.
Okay.
So we know that the time can be most exponential because after an exponential amount of time, you will exhaust all the possible states of the memory which you allocated. But aside from that, it can be. But yeah, that's a lot of time. So this class contains a lot is a very powerful class in the sense that there's a lot of problems that you can solve in this complexity. So for example, what are examples of problems in PSPACE? So obviously P is contained in NP, and which is contained in PSPACE. So anything you can prove, you can also compute in polynomial space. Why? Because your algorithm can just literally go over all possible proofs until it finds a valid proof. Because the proof only takes, is only allowed to be that big, so it's enough to have polynomial space to accomplish this. Coin. So what is coin P? Coin P are the things you can disprove. So I mentioned before that proofs are asymmetric, right? Proving something is true and false is not the same thing. So if I can prove that something is false, it's also in PSPACE. Again, so I can just go over all the possible proofs. So PSPACE is a symmetric class. It doesn't matter, where if I take the complement of a language in PSPACE, it's still in PSPACE. Because if I have an algorithm that runs at polynomial time, I can add a not in the end before I output the result of the algorithm. That's trivial too. Another example is so this is some scary computer science notation, but what this p to the power of p sharp, what it actually means is counting problems. So what are counting problems? Problems where I need to count structures that have some properties. So that for each structure, it's easy to check, but I need to count how many of them are. For example, someone gives me a graph, and I want to know how many ways are there to color this graph in 4 colors, so that no 2 adjacent vertices have the same colors. I want the exact number of those things. So this can also be, and now I ask, okay, and now I can ask any question about this number. Like I want to ask, is this number divisible by 5? Whatever. Is the third digit of this number 7? It doesn't matter. Any property about this number I want to ask. This is going to be in PSPACE because, again, I can just go over all possible structures, like all the colorings of the graph. They only take polynomial space, so I just count them. Easy. Right. Another example is matching a regular expression. So I guess some people here are programmers, so probably you know what a regular expression is. So matching regex. So if you don't know what a regex is, then never mind. But if you know what a regex is, then you know that checking where a string satisfies a regex, that can actually take a lot of time. That's why you usually, if you work with regexes, usually pre-compile the regex, and then the compilation takes some time. But in runtime, it's quick. But if someone just gives you a regex and a string, then that's not something you can check in polynomial time in general. But in polynomial space, you can do it. It's just recursion. Just imagine that you kind of recursively going through all the things that the regex is composed of, and you can see that you never need more than polynomial space. Okay, so PSPACE is a really big class. But now, the really cool thing about PSPACE is that there is an alternative way to define it in terms of games. Not talk about memory at all, but only talk about games. Okay, and a priori it seems what's the connection to games, but it turns out that there is. So games. So what is a game? So think of something like chess, for example, or Go, whatever. So there are two players. So when I talk about games here, the intent is it's a zero-sum game between two players. It's not even zero-sum, just a win-loss game. The two players, they're playing, and well, in chess you also have a draw, but here let's suppose it doesn't really matter, but let's suppose there's no draw. It's either player 1 wins or player 2 wins. And they're taking moves one after the other. So player 1 takes a move, player 2 takes a move, player 1 takes a move, player 2 takes a move. It's full information. They see all the moves the other players took. We also assume that the number of moves, so there is some input X, which is like the starting position of the game or whatever. And then they take their moves, and the number of moves is not allowed to be more than polynomial in the size of this starting position. And there is some algorithm which knows how to check that the moves are valid and knows how to check that the game ended. And if the game ended, we know how to check who won the game, or white won or black won. So that's a game, basically. And every game can define a language. So how does it define the language? So it defines a language by saying from this starting position, does player 1 win or player 2 wins? So the language is the set of all starting positions for which player 1 wins. Okay. And it turns out that the languages you can describe in this way using games are exactly PSPACE. So in one direction, it's kind of obvious. If you have a game, then in polynomial space, you can check who wins. Why? Again, you just do recursion. Basically, just check the entire game tree. Just go through the entire game tree. Like you don't need more than polynomial space because we said that you're not allowed to have more than polynomial number of moves. So at every particular point of your recursion, you're somewhere in the game tree. You just need to remember the branch you're in. And yeah, so any game you can in polynomial space check who is going to win. But it turns out the converse is also true. So if you have any polynomial space algorithm, that there is a game such that player 1 wins if and only if if this algorithm outputs 1, player 1 wins. If this algorithm outputs 0, player 2 wins. So the way this game works is kind of like, well, I guess I've just said it in one sentence, but imagine that this is like the timeline, which can be exponentially long, of the computation of my algorithm. And now, so now one player is trying to prove that the algorithm outputs 1, and the second is trying in some sense to prove that it's false, the algorithm outputs 0. So the one that claims that outputs 1 says, okay, this is the state of the algorithm in the middle of the computation. And then the second player, if they're right, then right. But then the second player, if the actual output is 0, then they're lying about something. Either this is not the real state, or the state doesn't actually lead to 1. So the second player needs to challenge the first player and says, you're lying here or you're lying here. Either you're lying about the state or you're lying that the state leads to the output 1. Then once you're challenged, it's the turn of the first player. And the first player needs to give the state of the algorithm in the segment where it was challenged. And they continue in this way. And, because this reduces by a factor of 2 every time, then, and the length of this thing is just exponential, then in a polynomial number of steps, they will converge. And eventually, either one of them will be right or not. They will just end up with 2 consecutive states of the algorithm. And either the state truly leads to the other or doesn't lead to the other. So this determines who won the game. So, okay. So PSPACE equals games. That's actually a very easy theorem. So there's still some trick here, as you can tell, but relatively that's considered a really easy theorem. But the theorem I really wanted to talk about is the theorem IP equals PSPACE. So what's the relation between IP and PSPACE? PSPACE are those games or things that can be computed in polynomial memory. IP is things where you have an interactive protocol to prove something. So first of all, it's pretty easy to see that IP is contained in PSPACE. Because for any interactive protocol, you can just kind of simulate all the ways this protocol can go and count and compute the exact probability of success in polynomial space. It's kind of like going through all the branches of a game tree, sort of. So this side is easy. But it turns out that they're actually equal. And this is a highly non-trivial theorem that was proven by Adi Shamir. So, so think conceptually, what does it mean now? It means that if we take a game, such as chess, for example, so as long as the game is not allowed to be too long, so in chess, I think there's some bound of some few thousand moves is the length of the maximal legal chess game, something like this. Then and there is there is some alien who has unbounded compute, and the alien knows what the real answer. The alien knows who wins in chess, or it's white or black. It means that there is some interactive protocol the alien could use to prove to you, even though you don't trust the alien is going to prove to you that white win, even though it's like a huge exponentially large game tree. You cannot go through the whole game tree, but this alien can just prove to you that white are going to win. And this is completely non-obvious because you could imagine something like, okay, maybe I will play chess against the alien, and every time the alien is white, they're going to beat me. But this doesn't prove anything, right? Because I'm not so powerful. I don't know the ideal gameplay. Maybe I just lose every time because I'm stupid, right? Or because I have bounded compute. It doesn't prove anything. But here, no, there is an actual way to prove to you, up to those probabilities, which can be as small as you want, that what happens. And this uses some trick called arithmetization, where you start with a Boolean formula and turn it into a polynomial over a finite field. And so it's some beautiful number theory. I think I was actually thinking of explaining the proof, but I think it might be like too much for this talk. So I think I'll just stop here, and maybe for people who are interested in the details of the proof, I can discuss later. Yeah.
So it seems like the proof you gave before that that everything that's a game is in PSPACE should work for.
No, not even close. I mean, the proof I gave before. What we need here is like okay, I will explain.
No.
So in the game I had before, both players have unbounded compute.
Right. Okay, good.
Okay, this is the answer. And here the verifier has bounded compute.
Yeah.
This makes it way more difficult.
More powerful.
So in the game I explained before, when I just turned the IP space problem into a game, both players, so it turned in a game in the sense that for ideal play, if you know who wins, this determines the output of the algorithm. But ideal play requires both players to have unbounded compute to find this ideal play. Whereas in IP, you have an interactive protocol where the verifier has bounded compute. The verifier is just an ordinary polynomial type algorithm. It's like a real algorithm you can actually code, you can actually write on your computer, and it will run, and it will work in some reasonable time. Only the prover has access to unbounded compute. So
what you're saying here is that it might be surprising that IP equals PSPACE, because in PSPACE there's unbounded compute, and in IP only one of the two sides has unbounded compute. Is this correct?
yeah, basically, sure.
Why would that be surprising? Because PSPACE, it has unbounded compute.
Mm-hmm.
But in IP, one of the sides is super powerful and has unbounded compute. The other doesn't. But why do we consider it surprising?
Because I mean the thing is, yeah, one side is super powerful, and
Yes.
the powerful side can easily solve this problem. This is not surprising.
That's
The surprising part is that they can convince me, even though they are untrustworthy, I don't trust them. I don't
Yes.
believe them. They can lie to me. And yet there is some protocol
Yes.
which, despite the fact that I'm, this bounded agent that can only use bounded compute,
Yes.
I can become convinced and I will know that the answer, despite the fact that I haven't, I know that this entity can be lying to me.
So the interactivity doesn't lose power. That's the point. You don't lose.
The interactivity is one against the other, right? Like the prover has unbounded power,
Yes.
but he can lie. Like I can prove something and then tell you why I proved
You're
it.
the verifier.
But lying. The whole point here is that you can verify it, even if I'm trying to trick you.
Yes.
Like you don't have access to full compute. I do, supposedly, and I could be lying to you. I could be trying to mislead you.
Yes.
But you are able to verify it anyway.
Yes.
I think.
Okay.
You say you have unbounded compute. I think you're lying.
I mean, you don't need to believe that it has unbounded compute for the product to work.
Can you give some examples, like how is it used and like what does it serve?
Yeah, so this theorem is, because the prover has unbounded compute here, it's not like a practical algorithm. It's not really, something you can use to, I don't know, to control traffic, or I don't know, for some practical purpose. It's just, I think, kind of a beautiful mathematical fact about the universe, kind of philosophically. It does have connections with things which have actual applications. For example, zero knowledge proofs, right? So the theory of zero knowledge proofs is kind of grows out of the theory of interactive protocols. So zero knowledge proofs are protocols that allow me to prove to you that I know something without revealing anything about what I know. So I can have like some secret knowledge. For example, I know I know how to color a particular graph in 3 colors or whatever, and I can prove to you that I actually know it, but you don't learn anything and you still don't know how to prove it. So this can be used in various, communications between parties that want to maintain secrecy and do things. Yeah.
The very practical application of that is there are a bunch of there's at least one newer cryptocurrency that specifically relies on zero knowledge proofs in order to guarantee anonymity, and so there are very concrete applications.
Yeah. So kind of this notion of interactive proofs, it produced a lot of ideas in cryptography, some of which are practical, but in itself is just, I think, an abstract, beautiful thing. I think one of the, I haven't explained the proof, so you can't really appreciate it, but I think it's one of the most beautiful, elegant theorems in theoretical computer science. Yeah.
Could you briefly explain, hopefully in a way we understand, how this fits into your research program? This is, of course, very,
it doesn't.
Okay.
It's not. I mean, it's not. Apart from the fact that it's like, theoretical computer science and complexity theory, which is quite relevant to my research program, this particular thing is not. Actually, there was some idea of using interactive protocols for something in AI alignment, which I forgot what its last name was suggested at some point, but I think it was forgotten. And there is actually some. Okay, if you brought up this topic, then there is actually some idea I had at some point, which I haven't done much with, but might still turn out to be interesting, where I showed that using the notion of zero knowledge proofs, you can show that there are some situations where an agent can exploit some of the computing resources in its environment in a way that only works when the agent can interact dynamically with the environment and not when you can just observe the environment passively. But it's kind of a mind. I don't know if that's really very important. That's not the reason I wanted to give. Yeah.
So you wrote earlier that NP is a subset of PSPACE. Do we know if it's a proper subset, or is it possible that NP is equal to PSPACE?
Yeah. So we don't know anything. Well, we know some things, but as far as what we actually know to prove, it is possible that P equals P space. And if P equals P space, of course, everything in the middle is also equals. But of course, it's widely believed that they're not equal. But we should.
But all three are not equal.
Yeah, it's widely believed they're not equal. We know how to prove, for example, that relatively to some oracles they're not equal. We know how to prove that relatively to a random oracle they're not equal. But I mean, this is actually an interesting kind of part of the story because, you know, complexity theory is really hard. It's really hard to prove anything. But one of the things that people do know how to prove sometimes is separation of complexity classes relatively to a random oracle. So an oracle is kind of a magic box that can give you, you know, ask it a question, it gives you an answer, and it's consistent. If you ask it the same question, it will give you the same answer. And if you have such a magic box, you might be able to do things with it which you cannot do without the magic box. Then random oracle is a box which just flips a coin to decide on its answer, but it's going to answer consistently. So if you ask the same question, so we flipped some coins in the beginning of time to construct the magic box. Okay, but then the magic box is fixed from there on. And then given this magic box, we have complexity classes like things computable in polynomial time with this magic box, things computable in polynomial space with this magic box, things, you know, for which there are proofs with this magic box, and so on. So that's called relativization in theoretical computer science. And in many cases, people know how to prove that for a random magic box with probability 1, P is not equal to NP. For example, this is proven, right? But this is actually interesting in this context because it was known before this theorem that relatively to a random magic box, IP is properly contained in P space. This theorem is actually false with respect to most magic boxes, but without the magic box, it's true. So I think historically, at some point, people believe maybe, you know, anything that's true for a random magic box is just also true absolutely. But this theorem is a good example why this is, you know, false. Yeah. Okay. So.